At the end of our last meeting, I said something prophetic. I realized that the potential difference that we call the voltages, the push, that causes charges to flow. And I speculate that if I increase the push, that is, if I increase the voltage, that the current should naturally increase, except the amount of current that I get also depends on the resistance of the materials. If the resistance increases, then I expect the current to decrease. And I implied that it sounded to me like there was a mathematical relationship there, and indeed there is. Today I'd like to talk about a few technical details associated with how we use the electrical effect in our technology in the context of electric circuits. We're going to analyze electrical behavior for the next few discussions in the context of electronic or electric circuit diagrams. A circuit diagram is more of a schematic. It doesn't represent the physical reality of what's happening, but sort of the logical connection between the ideas. And in circuit diagram, there's a kind of conventional iconography, if you like, a selection of symbols that are more or less universally used. It turns out, just like our systems of units, there's a little bit of difference between the way Europeans handle it and the way we do in the United States, and some variations in the East as well. But by and large, there's a conventional symbol, for example, that I would put in an electrical schematic for a battery. And this is the international symbol right here. You'll see me using this symbol as we go forward to represent a source of potential difference. Now, it doesn't particularly matter to me where that potential difference is coming from, whether it be a battery or a solar panel or even a static electric potential difference. I use the same symbol. This symbol is actually simplified from what it used to look like. You see here it has two horizontal lines associated with it. It used to have more than two horizontal lines, and sometimes people still use the version of the symbol that has more horizontal lines. The reason why is some of the first modern batteries that were created, there's archaeological evidence of batteries way back in antiquity, but the first really modern example of a battery was Alessandro Volta, who took, he had a wooden rod, sort of a stand, and he would take a disc with a hole in it of a metal, and he would drop that metal on there, and then he would put some cloth on that was soaked in salt solutions, another disc of metal and more salt solution, and another disc of metal and salt solution, and he would stack it up in what was known as a voltaic pile. He then, and on one particular occasion, took it to the court of Napoleon and demonstrated that if he piled them up high enough, there would be enough electrical effect that he could stab frog legs with it, and the frog legs would twitch, suggesting that there was electrical effect that was associated with the animation of the human body. And there's quite a bit of very legitimate speculation that this is where Mary Shelley got the inspiration for Frankenstein, that human beings might be animated after death, perhaps by the electrical effect. But at any rate, it's got two horizontal lines here, but notice that one of them is wider than the other. The wider is the high potential, and the narrow is the low potential, because this symbol represents a potential difference. There's a high and a low, and they're separate from each other. The high side of this battery icon is the positive side, and the bottom side is the negative side. I'm mentioning that not because there's necessarily a large accumulation of positive charge on this terminal and a large accumulation on the other, but this is conventionally how we do it. For example, you see a real battery here in the image, and you're familiar probably when you change the batteries out on your calculator or a device at home, that there is a raised portion on the one end of the battery and the other end of the battery is flat, and the raised end is labeled with a plus. That is the positive terminal of the battery, which is the wide side of the icon here, is the positive terminal. The other side then is the negative side. There's a lead to attach on the top, and there's a lead to attach on the bottom. When I attach wires or what have you in my circuit to the top, I'm offering the positive charges on the high side of the battery to flow. Remember, that's conventional current. I know it's actually the electrons that move. Everybody knows that. But by convention, I'm going to imagine that when I hook up this battery, that positive charges are going to flow out of the high end of the battery. And that is how that icon for electric potential difference works. I need another icon that will represent resistance. And so in circuit diagrams, again, pretty much all over the world conventionally, resistance looks like this. It's got this kind of zigzag to it, and the reason why is that's meant to give you the impression that when charges try to flow through here, they've got to zigzag back and forth, and that is in some way resistive or inconvenient to their motions. Don't push that analogy too far. The zigzag is part art and part physical reality. This little gizmo, when the charges flow in the top, they experience resistance until they flow out the end. Or the other way around, top to bottom, bottom to top, however way you connect it. Unlike a battery, a resistance doesn't have a positive side and a negative side as such. You can hook it up either way, and it works the same. When I look at a circuit diagram, the resistance indicated by this resistance icon could stand for just about anything. If you take an electric device at home and smash it on the floor, you will see that it contains little electronic devices known as resistors. They're just little electrical components that fit in, and they have a particular resistance, this many ohms, that many ohms, whatever you need to get the job done. But a resistor, shown here by this icon, could be any device that uses the electrical effect to practical purpose. For example, if I see the resistor icon in a circuit diagram, it might very well represent a light bulb. A light bulb, if you examine the end, the bottom end of this particular light bulb that screws into a socket, it actually has two connections. The threads themselves are made of metal, and they are separate from a metal nubbin on the end of the light bulb. There's a way into a light bulb, and there's a way out of a light bulb. Just like there's a way into this resistor icon, and there's a way out. Inside of a light bulb, there's an electrical filament that you can see here. It is a material that offers resistance to the flow of electrical current. It's not made of gold, because gold has a very low resistance. It's not made of copper, because copper has a comparatively low resistance. It's often made of tungsten or some other material that allows the current to flow but has a pretty high resistance. And what happens is that the flow of the charged particles through the filament in the light bulb generates heat. Enough heat, in fact, that it causes the gases that are trapped inside the glass bulb of the light bulb to glow. And that's how an incandescent light bulb works. That's just the case of the light bulb. If I connect a fan to a battery, cool myself down a bit, that fan has a resistance. Your oven has a resistance, your dryer has a resistance, your phone has a resistance. And all those resistances, when I draw circuit diagrams, are represented by a zigzag. Some of them have their own icons, little specialty icons. In some cases, there is actually an official icon for a light bulb. Or I could just put in a zigzag indicating some resistance. Electrical current is invisible. So if I set up some sort of electrical effect, for example, I could just go back to this generator, which I used in the last discussion. I crank the handle, and I see that the light bulb lights up. There must be some current, but I can't see it. So I need a device for measuring current in the same way that I need a device for measuring space. I use a ruler. I have a device for measuring mass. I use a pan balance. every physical quantity of interest in my universe that ends up as an SI unit, I have a stopwatch for measuring time. I have a device for measuring it. Well, I have a device for measuring current. It's called an ammeter. Well, in this case, this is not just an ammeter. This is what's called a multimeter. It measures all kinds of stuff. It measures voltage, current, and resistance, but it also has lots of features. You can see on the dial there are lots of different settings and whatnot. It is the electrical engineer and the electrician's tool to use this to measure all of those quantities. In the diagrams that you'll see me make over the next few discussions that we have, my meter will just be a box that reads the value. That's not sort of an official icon. You won't see that on international circuit diagrams or anything. It's just what I'll be using to indicate the value of the current, because I can't see the current in any given physical situation. Electrical circuits form complete loops. The etymology of the word circuit comes from circuital, which literally means loop. So the word circuit itself, as in electrical circuit, implies a complete closed path. Now, this circuit is not doing anything. You can see that my meter is reading 0 amps. You can see that my meter is reading 0 amps here. I've got a battery with a positive side and a negative side, a high side and a low side, and I have some resistance. Now, phenomenologically, here's what happens. Because of the potential difference, charge will flow around this circuit. Think of the wide side of the battery as high. Positive charges go from the high side all the way around the circuit to the low side, just like a ball rolls down a ramp from the high side to the low side, just like water flows downhill from the mountain to the ocean. The potential difference creates the push that is the cause of the current. There's two important points that I want to make about this, however. They're relatively simple, but they're critically important to understanding. Once the charges get to the bottom, they need to get back to the top again. When a ball rolls down a ramp, I have to pick it up and do work on it to raise its gravitational potential energy again so that it will roll down the ramp. I have to do that. Pick it up, put it up high, and let it roll down. Pick it up, put it up high, and let it roll down. When the water goes from the mountain to the ocean, the sun evaporates that water that goes up into the sky and falls as rain in the mountain so that the water can run back down again. The energy of the sunlight increases the gravitational potential energy of the water so that it can flow from the high place to the low place, and that water cycle is repeated. Well, when the charged particles go from the high side of the battery to the low side of the battery, they need to be lifted back up again. Not in terms of gravitational potential energy, in terms of electrical energy. When charges make the circuit, their energy needs to be judged. The chemical reaction inside the battery lifts the electrical energy of the charges so that they can do the circuit again. So the first critically important point of understanding the nature of how charges move around a circuit is that the battery is there to increase their energy, and then they go around the circuit and lose that energy, and then the battery increases their energy, and that process continues. If it weren't connected, then the charges would simply flow and pool, and the effect would not be continuous. Second critical point. Try not to imagine that when I connect the circuit together, charges slosh down here. Imagine that I have a bunch of water up here, and I get you to agree that up here in this tank of water is very high near the ceiling, that there's a lot of gravitational potential energy there. And you say, yes, I agree. There's a lot of gravitational potential energy. And I say, well, now I'm going to open the sluice. I enjoy the word sluice. I'm going to open the sluice, and now the water will flow. That is not how electricity flows. When I connect the circuit up and I create the path that allows electricity to flow, when one charge moves a little bit off the high side of the battery here, top side of the battery is the high side, when one charge moves off, it pushes all of the charges in front of it. Instead of there being water that starts up here and rushes down, when I complete the circuit, all of the charge in the circuit moves all at once. There's no lag. Well, technically there is a lag, but the lag happens at the speed of light. So for all intents and purposes, that is instantaneous. And the charge in the circuit starts going all at once. So what does it look like when I have a battery of a particular potential difference and a current, I have a battery of a particular potential difference and a resistance of a particular value of ohms. Oh, by the way, I forgot to mention here a comment on my own slide. When I draw a circuit diagram like this that has a voltage and a resistance, I use my imagination that the wires that connect them have no resistance, that they're ideal in some way. And of course, that's not specifically true. If I were to take a real battery and some leads and a light bulb and connect them together, the wires that I use to connect, they have resistance. They're made out of copper. Copper is a material that has resistance. But in a circuit diagram, we imagine that that resistance is so small that it can be neglected. If you're an engineer designing a device, then in the fine details, when you're about to create a product that's going to go to market and make you a profit so you can become rich, you're going to care about the resistance of the wires. It's going to matter. But here I'm not concerned about the resistance of the wires. I'll go ahead and assume that the wires have zero resistance. So here's my first circuit. I've taken a 5-volt battery and I've connected it to a 1,000 ohm resistor. Forgive the fact that it just says 1K. I know that the prefix K means 1,000, so that means 1,000. And I know that since it's a resistor, it's measured in ohms. So the 1K that I see there means 1,000 ohms of resistance. The fact that there's not an ohm written there is sort of like a quirk of the program that I used to create the graphics, so forgive me that. But I've got 5 volts. I got a 5-volt battery, and I connected it to 1,000 ohms of resistance. And then I put my meter in there, and I see how much current does that get me? And the meter says 5 milliamps. That's 0.005 amps, 5 milliamps of current, because milli is 10 to the minus third. Those prefixes, they still come in handy all the time in all of my science. So if I have 5 volts and 1K and I measure how much current I get, it's 5 milliamps. Maybe that's a surprise, maybe it's not, but that's a fact. That's what happens in the laboratory. I'm curious what happens if I double the voltage, keeping the resistance the same. You can see here I still have a 1K resistance, but I've doubled my 10 volts. Well, I can see from my measurement that when I double the voltage, I double the current. Now, I had previously qualitatively described this. I had said, I think that if I increase the voltage, the current will increase. And what I've discovered by actually making a measurement is that when I double the voltage, the current doubles. We've encountered in our studies relationships that go according to the square, and there are relationships in science that go according to the cube or the cube root or the 2/3 power or whatever, some funny relationships. But this relationship appears to be linear. If you double the voltage, it doubles the amount of current that you observe in the circuit. But the voltage is not the only thing I have control over. I can also change the resistance. So I'm going to keep this circuit here on the left the same, 5-volt battery and 1,000 ohms of resistance, and I'm going to change the circuit on the right. In fact, what I'm going to do, keeping the voltage 5 volts, is I'm going to double the resistance. Now, qualitatively, I feel like if you increase the resistance, that should decrease the current that you observe. And indeed, it's true. When I hook my meter up, 5 volts and 2,000 ohms, I get 2.5 milliamps. The current is actually divided in half. So it's also a linear relationship, but inverse. Increasing the resistance, decrease the current. It completely matches my phenomenological expectation of what's going to happen, my qualitative interpretation of the situation. But now it's quantitative. Doubling the resistance while keeping the voltage the same halves the current. And as I said, the end of the previous lesson, it seems to me that there's a mathematical relationship. And there is. The relationship is called Ohm's Law. And when we work with Ohm's Law, we do a thing that you might find a little annoying at first. Potential difference is delta V. Potential difference is delta V. But when we do electric circuit analysis, we never consider the potential, just the potential difference. So instead of writing delta V, just because, honestly, because we're lazy, we're human beings, we're lazy. Instead of writing delta V, we just start writing V, the voltage, is equal to the current multiplied by the resistance. Not as famous an equation as F equals ma, but close, because of how much of our technology in modern civilization is based on our understanding of how we can control the electrical phenomenon. V is equal to IR, Ohm's law famously. So it's true, I can go into the laboratory with my multimeter and measure things and find out the results of any particular combination of voltage and resistance that I'm interested in, but now I can also do it theoretically. Like I can calculate in advance. How much current should I expect when I do this? Before I actually do it and start a fire that burns the house down. I've taken this equation and done the two simple algebraic manipulations. I don't know why, I just sort of did that impulsively when I created this slide, that I can rearrange it and solve for the current and the resistance. Whatever I have, I can find what I'm looking for. So here's just an example to see if it matches our expectation. Imagine that I have a 6 volt battery and I connect it to a 5,000 ohm resistor. Just a little side comment that I want to mention. You might wonder, in order to make it simple for all of us, why didn't I use a resistor that was just 5 ohms? Why not just say 6 volts and 5 ohms? Well, I was gonna do that, but then I just couldn't bring myself to do it. I chose to make it 5,000 ohms, and the reason why is that in reality, when you go into a laboratory, if you were to take 6 volts and connect it to a laboratory resistor of 5 ohms, it's going to melt. That's a very, very melty situation. Because it turns out, in practical terms, 5 ohms is a very small resistance. In order to have safe currents that I can work with without setting things on fire, burning myself, or shocking myself, I really need high resistances so the currents are low enough that they're not dangerous currents. I don't want to support dangerous currents, going to hurt somebody. Remember I said that you need 100 milliamps to be dangerous. Well, by choosing 5,000 K as my resistance, I'm well under that. So even though it's up on the screen and can't hurt us, I have designed the circuit in such a way that it's very safe. But does it match my expectation? If the voltage is 6 volts and the resistance is 5 kiloohms, what do I expect the current to be? Well, if V is equal to IR, then the current is the voltage divided by the resistance. And 6 divided by 5,000 is 1.2 milliamps. But if I knew I had 1.2 milliamps and I multiplied by 5,000 ohms, I would get 6 volts. It's all consistent all around. The thing that I don't know, I can find using Ohm's law in terms of the things that I do know. As long as I know two things, I can find the other one because of this very, very simple relationship between voltage, current, and resistance known as Ohm's law.